This lecture is going to be over chapter 29, sections 5 through 7. We're going to be looking at semiconductors and how they work. So a semiconductor is a material with an electrical resistivity that is intermediate between those of good conductors and good insulators, hence the word semi. A hole is going to be defined as a vacancy in a bond where there would normally be an electron. The hole acts like a positive charge. And in N-type semiconductors, the conductivity is due to the motion of the electrons, and P-type holes act as the moving charges. So we'll get to describing all of that here in just a second. So the concept of energy bands and solids offers us additional insight into several properties of solids and is useful for understanding the properties of semiconductors, which we'll see in the next section. Suppose we have a large number, n, of identical atoms far enough apart that their interactions are negligible. Every atom has the same energy level diagram. You can draw it for the entire system. It looks just like the diagram for a single atom, but the exclusion principle applied to the entire system permits each state to be occupied by n electrons as opposed to just one. Now let's push them together. Because of the electrical interactions in the exclusion principle, the wave functions, especially those for the valence electrons, begin to distort. And the energy levels also shift somewhat. Some move upward, some move downward, depending on the environment of each individual atom. Thus, each valence electron state for the system, formerly a sharp energy level that could accommodate n electrons, splits into a band containing n closely spaced levels. Ordinarily, n is very large, on the order of Avogadro's number, if you remember that. So we can think of the levels as forming a continuous distribution of energies within a band. Between adjacent energy bands are gaps or forbidden regions where there are no allowed energy levels. The width of a gap is going to be called the band gap. So this is what we're seeing. We've got a filled valence band. We've got an empty conduction band. We've got a large energy gap here. So the inner electrons in an atom are affected much less by nearby atoms than the valence electrons are, and their energy levels remain relatively sharp. So what does that have to do with electrical conductivity? In insulators and semiconductors, the valence electrons fill completely the highest occupied band, or the valence band. The next highest band, called the conduction band, is completely empty. So you've got the valence band, you've got the conduction band. The energy gap separating the two may be on the order of 1 to 5 eV. So the electrons in the valence band are not free to move in response to an applied electric field. To move, an electron would have to go to a different quantum mechanical state with slightly different energy. But all the nearby states are already occupied. The only way an electron can move is to jump into the conduction band. So jump from here into here. This would require an additional energy of a few electron volts, and that much energy is ordinarily not available. The average energy available from thermal motion is roughly about 1/40th of an eV, which is not enough to get things moving. The situation is like a completely filled parking lot. None of the cars can move because there's no place to go, and a car would have to jump over the other cars in order to move. However, at any temperature above absolute zero, the atoms of the crystal have some vibrational motion, and there is some probability that an electron can gain enough energy from thermal motion to jump to the conduction band. Once in the conduction band, an electron is free to move in response to an applied electric field because there are plenty of nearby empty states available. There are always a few electrons in the conduction band, so no material is a perfect insulator. Furthermore, as the temperature increases, the population of the conduction band increases very rapidly. A doubling of the number of conduction electrons for a temperature rise of 10 centigrade degrees is typical. With metals, the situation is different because the valence band is only partially filled. The metal sodium is an example. For an isolated sodium atom in the ground state, the valence electron is in a 3s state. There are 3p excited states at about 2.1 eV above the 3s ground state. But in the crystal lattice of solid sodium, the 3s and 3p bands spread out enough that they're actually overlapping, forming a single band that is only 1/4 filled. The situation is similar to that shown up here, where you've got, let's see, you got a semiconductor here has the same band structure as an insulator, but a smaller gap. And a conductor has a partially filled conduction band. Electrons in states near the top of the filled portion of the band have many adjacent unoccupied states available, and they can easily gain or lose small amounts of energy in response to an applied electric field. Therefore, these electrons are mobile and can contribute to electrical and thermal conductivity. Metallic crystals always have partially filled bands. In ionic salt crystal, by contrast, there are no overlapping of bands. The valence band is completely filled, and the solid sodium crystal is an insulator. The band picture also adds insight into the phenomenon of dielectric breakdown, in which materials that are normally insulators become conductors when they're subject to a large enough electric field. If the electric field of a material is so large that there's a potential difference of a few volts over a distance comparable to atomic size, then the field can do enough work on the valence electron to boost it over the forbidden region and into the conduction band. Real insulators usually have dielectric strengths much lower than this because of structural imperfections that provide some energy in the forbidden regions. All right, so there's that. Now let's go to semiconductors. All right, so we've already discussed what a semiconductor is. The tremendous importance of semiconductors in present-day electronics stems in part from the fact that the electrical properties are highly sensitive to very small concentrations of impurities. So now, silicon and germanium are group 4 elements of the periodic table. In other words, if you look at the column of the periodic table, you'll see those two in there. Each has 4 electrons in the outermost subshells, 3s and 3p levels for silicon, 4s and 4p for germanium. Both crystallize in the diamond structure with covalent bonding. Each atom lies at the center of a regular tetrahedron, forming a covalent bond with each of its 4 nearest neighbors at the corners of the tetrahedron. All the valence electrons are involved in the bonding. The band structure has a valence band, which at absolute 0 would be completely filled, separated by an energy gap from a nearby conduction band. So you can see here, at absolute 0, a completely filled valence band is separated by a narrow energy gap of 1 eV or less from a completely empty conduction band. At ordinary temperatures, as shown here, the number of electrons, a number of them are excited into the conduction band. So in other words, they go from here to here. And that's what it's talking about here. At low temperatures, these materials are insulators. Electrons in the valence band have no nearby levels available into which they can move in response to an applied electric field. However, the energy gap between the valence and conduction bands is usually small, compared with 5 eV or for insulators. Thus, even at room temperatures, a substantial number of electrons are dissociated from the parent atoms and jump the gap into the conduction band. And that number increases with increasing temperature. So when an electron is removed from a covalent bond, it leaves a vacancy where there would ordinarily be an electron. An electron from a neighboring atom can easily drop into this vacancy, leaving the neighbor with vacancy. In this way, the vacancy is usually referred to as a hole, can travel through the crystal and serve as an additional current carrier. A hole behaves like a positively charged particle, even though the moving charges are electrons. It's like describing the motion of a bubble in a liquid. In a pure semiconductor, holes and electrons are always present in equal numbers. When an electron field is applied, they move in opposite directions, which you can see here. This conductivity is called intrinsic conductivity to distinguish it from conductivity due to impurities. So you can see here a motion of the electrons in the conduction band and of holes in the valence band. These are the electrons in the conduction, and these are the holes in the valence under the action of an applied electric field. So the parking lot analogy we mentioned earlier helps to clarify the mechanisms of conduction in a semiconductor. Covalent crystal with no bonds broken is like a filled floor of a parking garage. No cars or electrons can move because there's nowhere for them to go. But if one car is moved to the empty floor above, it can move freely, and the empty space it leaves also permits other cars to move onto the nearly filled floor. The motion of the vacant space corresponds to the hole in the normally filled valence band. So for impurity, suppose we mix into melted germanium a small amount of arsenic, the next element after germanium. The deliberate addition of impurity elements is often called doping. Arsenic is in group 5 of the periodic table. It has 5 valence electrons. When one of the electrons is removed, the remaining electron structure is essentially that of germanium. The only difference is that it is scaled down in size by the insignificant factor of 32/33 because the arsenic nucleus has a charge of 33 rather than 32. An arsenic atom can comfortably take the place of a germanium atom in a lattice. 4 of its 5 valence electrons form the necessary covalent bonds with the nearest neighbors. The 5th valence electron is very loosely bound with a binding energy of about 0.01 eV. In the band picture, this valence electron corresponds to an isolated energy level lying in the gap, 0.01 eV below the bottom of the conduction band. This is called the donor level, and the impurity atom that is responsible for this is the donor impurity, which this is what it's referring to. So all group 5 elements, nitrogen, phosphorus, arsenic, antimony, and bismuth, can serve as donor impurities. Even at ordinary temperatures, substantial numbers of electrons in donor levels can gain enough energy to climb into the conduction band, and they're free to wander around the lattice. The corresponding positive charge is associated with nuclear charge of the arsenic atom. It is not free to move, in contrast to the situation with electrons and holes in pure germanium. This positive charge does not participate in conduction. At ordinary temperatures, only a very small fraction of the valence electrons in pure germanium are able to escape their sites and participate in conduction. The concentration of arsenic atoms, as small as 1 part in 10 to the 10, can increase the conductivity so drastically that conduction due to impurities becomes the by far dominant mechanism. In this case, the conductivity is due almost entirely to negatively charged electronic motion. We call this an N-type semiconductor with N-type impurities. Adding elements from group 3 with only 3 valence electrons has an analogous effect. An example is gallium. Placed in the germanium lattice, the gallium atom would like to form 4 covalent bonds, but only has 3 outer electrons. But it can steal an electron from a neighboring germanium atom to complete the required 4 bonds. The resulting atom has the same electron configuration as germanium, but is larger by a factor of 32/31 because the nuclear charge is 31 instead of 32. And that leaves the neighboring atom with a hole or a missing electron, which can then move through the lattice, just as in intrinsic conductivity. That stolen electron is bound to the gallium atom in a level called an acceptor level of about 0.01 eV above the top of the valence band, right there. The gallium atom thus completes the needed 4 covalent bonds, but has a net charge of -e because there are 32 electrons and only 31 protons. In this case, the corresponding negative charge is associated with the deficiency of the positive charge of the gallium nucleus. In this case, the corresponding negative charge is not free to move a semiconductor with group 3 impurities to, say, p-type semiconductor with p-type impurities. And N is referred to as a donor, and a P is referred to as an acceptor. So now let's go to Semiconductor Devices. So one of the most important and obviously widespread applications of semiconductors is going to be the transistor. And it's an electronic device whose primary function is to switch or amplify electrical signals. Since 1947, the transistor has become the basic building block of modern electronics. Many different types of transistors, but one of the oldest and most widely used types consists of 3 layers of semiconductor material such as silicon. Different chemical additives called dopants are introduced into each layer in order to produce the desired electrical properties of the device. A separate electrical connection is then made of the 3 layers. In essence, the transistor behaves like an electronic valve. It is a typical mode of operation. The current flowing between the 2 outer layers of the 3-layer structure can be controlled by a much smaller current flowing into the center layer. Although this function may sound trivial, it is immensely useful in electronic applications. Since the 60s, semiconductor-based transistor devices have revolutionized electronics and communication industries. Because transistors are produced by simply overlaying specific semiconductor layers, they can be fabricated directly on the circuit substrate. This also allows them to be miniaturized. Indeed, large-scale integrated circuits can incorporate many thousands of transistors on a chip that is smaller than 1 cm squared. Such chips are found in cell phones, laptops, mainframes, that kind of thing. Semiconductors are used in other devices. In fact, one of the oldest and simplest examples of a semiconductor is a photocell. A thin slab of pure silicon or germanium is connected to the terminals of a battery. The resulting current is small because there are very few mobile charges, but now we irradiate the slab with electromagnetic waves whose photons have at least as much energy as the band gap between the valence and the conduction bands. This radiation corresponds to the photon energies in the visible or nearly infrared region of the electromagnetic spectrum. Now an electron in the valence band can absorb a photon and jump to the conduction band, where it and the hole it left behind contribute to the conductivity of the slab. Therefore, the conductivity and the circuit current increase with the intensity of the radiation. And detectors for charged particles operate on the same principle. When a high energy charged particle passes through a semiconductor material, it collides inelastically with valence electrons, exciting them from the valence to the conduction band and creating pairs of holes and conduction electrons. The conductivity increases momentarily, causing a pulse and current in an external circuit, and semiconductor detectors are widely used in nuclear and high physics energy research.